So we are playing with matrices, right? Matrix. So we try to convert everything in matrices. So matrix, Octave or MATLAB. Yep. So always we have to use matrices when we use Octave or MATLAB. So that's why if you don't know matrices, you know matrices. Now let's brush up our knowledge on matrices a little bit. So let's go to this node from the basic. So this is uh, a general rectangular matrix. It has how many rows? So this is the row number and this one is the row number. So how many rows? M number of rows and n number of columns. So m by n. So this is the dimension of the matrix. So this is called rectangular matrix. If the number of rows and columns are the same, then we say it is a square matrix, right? So in this course, we will talk about how to find inverse of these kind of rectangular matrix. So I think first year you learned how to find inverse for square matrix. So I think So in this course we will see you will understand what is the inverse of these kind of rectangular matrix, right? Square, so number of rows and columns are the same. Diagonal, so this is the main diagonal, but except the main diagonal elements, you have zeros of diagonal elements. Of diagonal elements are equal to 0. These are called off diagonal elements. These are called diagonal elements. So this is a 3 by 3 diagonal matrix. This is 2 by 2, 0. You have to fill every element is equal to 0 in 0 matrix. Identity, all diagonal element. So equal to 0. Triangular, upper triangle. So there are two kinds of upper and lower triangular matrices. So upper, so we discuss these things. The upper and below the main diagonal, all elements should be equal to 0. So this is called an upper triangular. This is lower. Vector could be one. It could be one row or a row or column. So you have only one array or single row or either single row or column, right? So if you have a row matrix, it is called row vector, and column matrix, it is called matrix having one column. So it's called column matrix or column vector. Otherwise, or you can say row vector or row matrix. So scalar, so the dimension of a scalar is 1 by 1 transpose. So these. So you can operate matrices, right? Can operate matrices. Let's add. When you add two matrices, you get another matrix with the same dimension. Look at the dimension. When you add these two matrices, make sure that these dimensions match each other, right? Okay. Otherwise, you cannot add or subtract two matrices, right? When you add or subtract two matrices, get the same dimension, right? Again, so this is then you can say this is a binary operation. Yeah, in linear algebra, yeah. And yeah, you can multiply two matrices. Yeah, again, you get another matrix, right? Yeah, so again, you get another matrix. But make sure that, yeah, so this is commutative. That means the way you operate, yeah, does not matter. The order of these two matrices. So A plus B is same with B plus A. Yeah, yeah, addition commutative holds, but the matrix multiplication commutation, yeah, commutative property does not hold. So we know that. Yeah, when you multiply two matrices, make sure that inner dimension match, right? Inner dimension and so number of columns. So this is number of columns should be number of columns of matrix A should be equal to number of rows of matrix B if you want to multiply. Yeah, these two matrices. Yeah, so we have learned first year. Yeah, so this is so you can find the elements in the resultant matrix. Yep, like this, you know how to multiply, uh, but the matrix division is not defined. Yeah, it's not defined, right? There is no such thing as division of matrices. Okay. So however, inverse, yeah. So we in the sense of so division. Yep. So actually, matrix multiplication is a group. Is a group. Yep. So let's say if you have real matrices, so this is n by n. Yep. So let's denote matrix of real matrices, and this is the dimension. Yep. So dimension n by n. Yeah. So this is the set of all. Yeah. This is the set of all n by n real matrices. Yeah. This set is this set is a group under matrix multiplication. Yep. Yep. So yeah, I think we are sure. Yeah, this is a group. Yeah. So if it is a group, yeah, so we know that if you so additive identity is identity matrix. Yeah, identity matrix, additive inverse. If you select any non-zero matrix. No, this is identity of the matrix multiplication. Yeah, so if you select any non-zero matrix, yeah, so it has an inverse. No, this is not a group, right? Is this a group? That's not all right. Okay. So you have learned algebra. Is this a group? Matrix multiplication. All right. Not inverse. Yeah. No, it is not a group by the for instance, yeah, this does not this is if this is additive multiplicative identity, yeah, so is this a group? Yeah, it is a group, but no, it is not a group. Yeah, it is not a group. So multiplication of two matrices. Yeah. So you get so Remember that matrix multiplication division is not defined, right? But so this is different stuff. Yeah, if you have a non-singular matrix, yeah, if you have a non-singular matrix, then yeah, there exists a matrix P such that A, B is equal to identity matrix. If it is non-singular matrix, yep, this also inverse can be defined for non-singular matrices, not for singular matrices, right? Yeah. So you know how to yeah. The other one, determinant. So you can check whether the matrix is singular or non-singular by computing determinant of the matrix, right? Right. Determinant is a scalar value function. It goes from the matrix space. Yeah, this is let's say this is the set of matrices. Let's assume n by n matrices, real matrices. From this set to I was disconnected. Suddenly, I sharing my screen now. I was disconnected suddenly. Yep. Yeah, determinant is a scalar value function. Yep. So from matrices, set of matrices to real value. Yeah. So if you have matrix, yep. So this gives you a real number, that of A. Yep. Right. It is denoted by one of these notations. Yeah. So some people denote determinant is this or this or this. Okay, determinant of identity matrix is 1, and the determinant of transpose matrix. Same with the determinant of sure, I use matrix 1 more. And determinant of product of two matrices is product of two. Determinant. They are determinants. Yeah, so these are basic stuff you need to know to follow to solve the linear system of linear equations. Yeah, so let me jump into minutes. Yep, so let's assume we have a very simple equation. This has so x is called the unknown, and these a and b are known. Numbers known. Constants. They are constants. A and b are constants, and x is called unknown. So this is a equation, simple equation in x, right? So x is unknown, right? So the solution of this equation, this simple equation, depends on these coefficients. These coefficients, these a and b, right? So for instance, if a is not equal to 0, that means you can divide that non-zero quantity. You can divide the entire equation by that non-zero quantity, then you can solve this for x. So if a is not equal to 0, so this equation has a unique solution, has a single solution. If this is equal to 0, what if this is equal to 0? Let's assume this one also equal to 0, right? both A and B are equal to 0, this x can be taken. Yeah, you can choose any value for x. You can substitute any value for x, right? So if A and B are both are equal to 0, so this equation has infinitely many solutions. Has any value? Yeah, yeah. So you can put any number which satisfies the equation if both A and B constants are equal to 0, right? Let's assume A is equal to 0, but this guy is not equal to 0. So if A is equal to 0, yeah, so you know that, so we are dealing with real numbers. So because 0 is an additive identity, right? Yeah, when you multiply additive identity, we know additive identity as well. So actually R is a set of real numbers. It's a ring, right? So having this property R0, when you multiply this 0 element, so you get always 0. So therefore, this side, when A is equal to 0, this left hand side always equals 0. So what if the right hand side is not equal to 0? That is inconsistent. So that equation is inconsistent. So that doesn't make sense, right? 0 is equal to now something non-zero, which is cannot cannot happen, right? So therefore, so x does not have any solution. So when a is equal to 0 and b is non-zero, this equation does not have any solutions. So if when you are given a equation like this, so there are three possible cases: unique solutions, infinitely many solutions, or no solutions to this simple equation. Yeah, that is same with the system of equations. Yeah, that is same with the system of equations like this. So there are three cases. One of them is unique solutions, and no solutions, and infinitely many solutions. That depends on this if you write this system in matrix form. So you can separate coefficients and the unknowns separately. So you can write A is all coefficients. A is all coefficients of these equations, right? A consists of all coefficients. In first row of A consists of A11, A12, and dot 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 A1M. What is the dimension? Dimension is this is a number of how many equations are there? M number of equations. So this is and how many variables are there? M number of variables. So the dimension of the coefficient matrix is n by n. Square matrix, right? And so this is coefficient, and this is in this vector. This is a vector consists of all unknowns: x1, x2, 2, xm. So if you define this product, so make sure that this inner dimension is matched. So this is a row vector, column vector. Column vector. Consisting of x1, x2, xm. So this is this side, left hand side, which is same with the right hand side. is this is a constant, a vector. Yep. So consisting of, yeah, again this one also a column vector consisting of, yeah, b1 up to bn. So yeah, you can rewrite this system. So this yeah, so dealing with this and this finite number of equation, instead of dealing with this finite number of equation, we are dealing with this simple condensed form. This equation ax equal b. Yep, simple form. Ax is a vector. Yeah, b. Very easy. We don't need to put, yeah, write everything, yeah, buses and all terms. Yeah, this is the condensed form, matrix form, right? So if you are given a system, all the time try to write matrix form, right? Coefficient matrix and the variable column, yeah, a set of unknowns, yeah. So which is a column matrix, and the right hand side of the set of equations, yeah, or yeah, right hand side. Okay, solutions to this system, yeah, depends on this coefficient matrix and the right hand side. These two matrices, right? If you have a full rank matrix, or if you have a full rank, that means if you have a non-singular matrix, yeah, this system, this kind of system, these kind of yeah, this system has a unique solution. If you have a full rank matrix, coefficient matrix, right, or non-singular matrix, right? So first case is the first case. So there are three cases. Yeah. So yeah, first case, if this is non-singular, this system or non-singular or full rank matrix. Yeah. So if you have linearly independent rows, so rank of this matrix is yeah, full rank. Yeah. So full rank, all are independent rows or columns, right? So then this system has a unique solution, right? If you have, let's say, not full rank, let's say the rank, full rank is, let's have, yeah, so this is m by n. So if this is full rank, then rank of A should be equal to m, right? If it is full rank. If it is not full rank, yeah, that means rank of A, rank, yeah, rank of A is less than m. Yeah, so this matrix is singular, or not full rank. Yeah, this system has infinitely many solutions, right? Infinitely many solutions. And the other case, it could be either, sorry, not infinitely many. If your system, yeah, this coefficient matrix is not full rank, uh, either it is infinitely many or no solutions to the system, right? Don't know, you have to check the consistency of the equation. So, right? So if this matrix is full rank, this system has a unique solution. If this matrix is not full rank, yeah, rank which is lower than n, then it could be either. So system has either infinitely many solutions or no solutions, right? So that depends on the right hand side, right? Make sense? Does that make sense? Cool. Yep. So I entered matrix. If I want to find the dimension quickly, so these are basic syntaxes. Yeah, let's play with these. Yeah, size. Make sure that you use this dimension if you want to catch both the number of column number of rows and columns. Yeah, you can define yeah number of rows, a number of columns. Yeah, so just give names. Yeah, then put size. Yep, yep. So then you have number of rows and columns like this. Okay. Let's find the rank of the matrix. Rank matrix A. Okay, it is a full rank because it is a square matrix, and it consists of uh, 4 rows only. So there are 4 independent rows. If so this is a full rank matrix. If you have a system with this coefficient matrix, yeah, you have a unique solution. Full rank, if you find the determinant of A, it is non-zero. Yep, it is non-zero. Non-zero. So therefore, this is non-singular. There exists inverse matrix for that. Yeah, if you want that. Find inverse matrix as well. Yeah, so there's a system. Let's define the right hand side. I define the right hand side. Any right hand side. Right hand side like this. Yep. So how many equation do we have? 4. So we have 4 numbers, column matrix or column vector consisting of 4 elements. Yeah, let's put any numbers because this matrix is non-singular or full rank or full rank. Yep. So if you define any right hand side, you have unique solution. Yep. So any we'll see the output. Yeah. So let's press. So because A inverse exists. Yep. So the solution would be A inverse. Yeah. Because it is full rank and row space. Yeah, rows are linearly independent. So linearly independent. Yep. So A inverse X times B. Yeah. Like that you have a single solution. Single solution. Right? In other words, unique solution, right? Unique solution or one solution. Right? So the solutions depends on the matrix, coefficient matrix, right? If it is non-singular, yeah, definitely this system has a unique solution. If it is, let's consider an example which is not full rank. Yeah, let's define. Yeah, so I'm pressing up arrow keys up. So if you want to take the previous comments you type, you can get pressing arrow keys, up or down arrow keys. So I'm defining linearly dependent row, linear dependent row. So this row depend on so if you find the rank, what is rank? So less than 4. It is not full rank. Why? So these two rows are not linear independent. So this row depends on this. So this can be written. Yeah. So this can be written in terms of the row trick because of that. Yeah. So you don't get full rank. When it is the case, there are two possibilities. Either the system has infinitely many, or no solutions, no solution. That depends on your right hand side. Okay, that depends on these two cases depends on your right hand side. So let's define a right hand side. Okay, right hand side. So so this was our, so for this, okay, for this right hand side, so yeah, let's find determinant. If you find the determinant, what happens? Determinant is 0. Yeah, so look at this here. So yeah, that depends on this right hand side. So yeah, so it could either infinitely many. So because these two rows are dependent, that's why you get 0 for determinant, right? If these all are independent, you don't get 0. That depends on right hand side. Yep. So if you find inverse, okay, there's reduce form of thing. Yeah, right. So this is built-in function. If you row reduce echelon form of A, right? So you can reduce this A, this matrix A, by performing row operations. If you perform row operations to this system, so there, what are the operations? What are the row operations? You can swap any two rows. You can swap or you can interchange any two rows. If you interchange any two rows, what do? You interchange these two, any two equations. If you swap two rows, means you swap any, let's say you swap first row and the second row. You put the second row here in the matrix form. In the for that, sorry, so this is your coefficient, and this is your right hand side. We consider both coefficient matrix and right hand side together, right? So which is called augmented matrix. Augmented matrix, right? I will denote as this. My augmented matrix consists consists of the coefficient matrix and no, and my column matrix, right hand side. Yeah. So let's. I want to see the output. So then I don't enter semicolon. Yeah. Yeah. So this is called the augmented matrix. The coefficient matrix with the right hand side. This is the right hand side, and this is your coefficient matrix, right? Okay. All right. 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 So if you interchange, you can interchange any rows. If you interchange any rows of augmented matrix, what do? You interchange the corresponding two equations. When you do that, does that affect to the set of solutions? I'm asking you that. So when you interchange any two equations, will that affect to the set of solutions or solution of this? No, yeah, that's right. When you can consider the second one first. Yeah, you can write the second equation at the beginning, or you can put the first equation. You can interchange as you wish. Yeah, you can interchange. That is the first row operation. Yeah, that's right. Yeah, thank you. Yeah, that is the first row operation. You can interchange any rows. If you interchange any rows of augmented matrix, so the corresponding one is you are interchanging any equations of the system. When you do this process, that does not affect to the solution of the system, right? So that is one of row operations, and the other one is you can multiply. Yeah, so what is the other row operation? What is the other row operation? You can multiply any row by a, you can scale. You can scale any row. So that means you can multiply, yeah, you can multiply any row by a constant or by a scalar, right? So when you do, yeah, you just multiply some number from both sides. Yeah, so I just multiply 8 from this side, and I do the same to other side. Yep. So I did nothing because this cancels, right? So the second row operation is I can multiply. Yeah, I can scale any row of augmented matrix, right? So when you perform that operation, the solution set remains the same. You get the same solution, right? Get the same solution. Yeah, that does not affect to the solution of this system, right? Can scale any row, right? Any row can be scaled, and and there's another operation. Remember? Do you remember? There's another operation. You scale one of rows and add that add the resultant one to another row, right? Remember, if you want to get rid of this bugger here, yeah, okay. Let's say you have this simple aha. So this is a simple, yeah, okay, yeah. So yeah, if you want to get rid of this bugger here, X1, So yeah, so you multiply the second row, the entire row by -2, right? By -2, this would be 4, and this would be, yeah. And you add these together, then you can get rid of these two. And then you have this. No, I'm saying if you want to, yeah, if you want to remove this guy here, yeah, you multiply, yeah, so you multiply this. So you have to consider the augmented matrix, this coefficient with the right hand side. So you multiply the entire row by -2, right? Then I add that row to the first one, first row with first row. Then you get something, right? You get something. Then I replace the second row with that that thing, right? When you do that, yeah, that won't affect to the solution set of x equal b. So that means you can perform row operations, right? When you perform row operations, the solution set remains the same. Yeah, you get the same solution. So you get the same solution. If you perform any row operations, you get the same solution that won't be affected, right? That won't be affected by row operations. So you can reduce your original matrix. Is this your original matrix? Okay. So I will enter a type. Yeah, yes. So let me enter a different one. Yeah. So okay. Right. So let's assume this is I will call, yeah, augmented matrix. Oh, augmented matrix. That means this consists of the coefficient matrix. Which one is the coefficient matrix? This is my coefficient matrix. The augmented matrix consists of coefficient matrix, the right hand side of the system. Okay. 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 Let's assume this is your augmented matrix. Now, yeah. Yeah, now I can perform row operations. I can simplify this matrix. So, when you perform row operations, so you get the same solution. So here you have a solution. Here you have some solution. Let's assume x. You get some solution x. 1, 2, 3. Let's pretend this to be a solution, right? Yeah, when you perform row operation, after performing row operation, you can reduce this matrix to something, yeah, something low, upper triangular or lower triangular, right? Per triangular. So dealing with this matrix compared to this is simple. So this is a little bit difficult, yeah. So dealing with this simple matrix, yep, so simple than the previous one, but you get the same. So when you find this solution, again you get this solution. So performing row operation won't affect the solution set. Okay, you get the same thing. Okay, that is the learning today. Yep. So if you have a system, always try to reduce the system to a row reduced echelon form or echelon form, right? So then we find the solution. Then we find the solution. Okay, okay, this is my augmented matrix. Yeah, let's find, okay. So inverse, let's find the inverse of, first of all, let me find the rank of augmented matrix. Yeah, full rank. Okay, Unix solutions. Yeah, this is full rank. Now let's look at the coefficient matrix. Yeah. So it is from column 1 to column 1 to 3. Uh, 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 as this. Why it is so I'm confusing with yeah, so now let's remember what is the syntax if you want to retrieve. Yeah, so okay. Yeah, so this is your coefficient matrix augmented. Look at this if you want to see the coefficient matrix. Yeah, this is your coefficient matrix here. This bit, and this. So then I found the rank of the coefficient matrix, which is 3, yeah, full rank. Okay, full rank, no worries, you have a full Unix solution to this one. So how do you find, yeah, yep, so how do you find the solutions? Yeah, let's find the solutions. Yes, the coefficient matrix and the right hand side. Right hand side. What is the right hand side? Right hand side of the augmented. Yeah, I want to read this. Yeah, this column. Which one? Fourth column. Yeah, let's retrieve fourth column. Only fourth column. All rows. Only four column. Yeah, fourth column. Yeah, this is the solution to this system because yeah, this is augmented matrix. This is the right answer. The augmented matrix consists of coefficient matrix and right hand side, and this is because this is full rank. Yeah, this is invertible. Yeah, so then we can find the unique solution. Now I'm going to reduce this augmented matrix and find the solution. Check the solution again. So then you will see that you will get the same solution. Because when you perform row operations, yeah, the solution set won't be affected. Yep. So there's a built-in function in Octave in yeah, row reduce echelon form to get row reduce echelon form, right? So I will name this. I will put a label. Let's call C. Yep. So row reduce echelon form of my augmented matrix. Yeah. This is my row. Here we go. So row reduce echelon form. Okay. This is my row reduce echelon form. So this is my coefficient matrix would be this. Here I have invisible variables x1, so column vector x2, x2 and the last x3. And this is my right hand side. So you can see that x1 is equal to negative 2, x3, x2 is equal to 2, x3 is equal to negative 1. You get the same solution. So here you reduce this the augmented matrix using row operations, right? So when you perform row operations, the solution set remains the same. So that won't be affected, right? By performing row operations. So that is the learning. That is the learning today. Yeah. So when you perform row operation, so you don't touch. So you can preserve this original solution. Here, this is the solution. Okay. Make sense? Does that make sense? Stop reduce. Yep. So yeah. So someone who doesn't know a linear system, let's define a linear system. Yep. So here a linear system or linear equation. So here this consists of n number of uh, unknowns. So xi's are unknowns. How many unknowns are there? 1, 2, 3, up to n. Yeah, there are n number of variables. We call it variable, or you can call it unknowns or variables. So here, yep. So or you can call it degree of freedom of the equation. So n degree of freedom, degrees of freedom in this equation. Right, sorry. Yes, there are n number of unknowns, but look at the but look at the exponent and the in front term. So this is the in front term. Front term. So all are real numbers or complex numbers. So these are constants. Scalars. Right. And look at the exponent. Exponent is equal to exponents. So it's equal to 1. So that's why we call it. It is a linear equation. It is called a linear equation. This does not have a product of any unknowns. Here you don't have these terms x1, x2 terms or product of unknowns, right? We don't have linear equation that doesn't have the product of unknowns involving trigonometric. So exponential. This is not a so this is not a linear term. So you can express this as a Taylor expansion. So you know that it is a power series. So you can express this as power series. So in power series, you have x1 cube, x squared, x2. So this is not a linear exponential, trigonometric, not a linear. Function is not linear. These are non-linear. Functions, non-linear terms. So here we don't have those functions, but just only x's. This is a linear equation. Right? This is a linear equation, constant terms and exponents as well. But if you look at this one, no, not this one. So this is not a linear, non-linear. Here in this equation, you have product of two unknowns, a finite number of unknowns. So product of, so it could be x, y, z, or, so product of unknowns. So this is not a linear, this is called non-linear. And here another example. Yep. So sine is not a linear function. It is a non-linear function. If you express sine as a power series, yeah, it is a non-linear. Yeah, so non-linear. So this is non-linear. So this is a non-linear equation. We call, yeah, this is a non-linear equation. Yeah, this one also non-linear one. No reciprocal of unknowns. Okay, exponential non-linear. But so sine of pi is a constant. It's a number. It's a irrational number. Irrational number. Yeah, sine of that. Yeah, pi is a number. This is a constant. Because of that, yeah, this equation is a linear. So, right? Yeah, this one, yeah, number times your unknown, yeah, exponent is one. Yeah, so linear equation. So you can identify whether as a equation, whether an equation is linear or non-linear. Alright, okay. Yeah, solution of a linear equation. Yep, so I discussed that. Yep, so yep, I discussed this. Yeah, your degree of freedom is 2, so we have only one. One equation. This has infinite limit. Yeah, so you can write the solution set. With yeah, so when you solve this for x1, 4 minus 2x. Yep, so this is a variable. Yeah, you can insert any value for this. Yeah, that's why I call, I put the letter for that. Yeah, so t is a parameter. A parameter, when you change this parameter, you get x1 according to that value of parameter, you get solution of x1. Yeah, so x1 is this, x2, yeah, so like that you can see t is a parameter, it belongs to real numbers. Yeah, there are infinitely many solutions. Yep, we discussed already. Yep, so here, so graphical representation. Yeah, if you have so coefficient matrix is singular, right? So that means if you draw, you can visualize this, right? So if you plot this straight line, yeah, this is it has two variables. Yeah, you can plot it has two variables x and y. Yeah, you can plot this curve. Yeah, so when you plot this curve, you get a straight line. Yeah, because it is you have linear terms y equals mx plus c, right? And this one also a straight line, and you have a different slope and different intercept, right? So which is the slope and intercept different from the previous one because of that. So two lines are intersecting at a point. Yep. So this is the common point, common for both. Yeah, both lines. Therefore, this is the solution. This is the solution to this system. The system has a unique solution. Yeah, if the straight lines, if you have 2 by 2, yeah, so this simple system, yeah, you can visualize that. If what if these two lines are parallel, you cannot find any common points for these two straight lines. So therefore, no common points or no solutions to this system. And what if those two lines coincide, right? So you can find infinitely many common points. So the system has infinitely many solutions like that. You can visualize three-dimensional case, yeah, three variables as well. Yeah, so very simple. Yeah, so takeaway, the takeaway point is if you have a system A, X, B, right? So this is the variable, yeah, vector, and this is right hand side of the system of equation. The takeaway is this one. So you have system, yeah. So try to reduce, yeah, try to reduce. Consider the augmented matrix. Consider both coefficient as well as the right hand side. This is called augmented matrix. Yeah, reduce. So this is again, yeah, when you combine the coefficient and the right hand side of the system, yeah, again you get a matrix. Yeah, this is called augmented matrix. Yep. So to find the system, yeah, always reduce this augmented matrix to a simple, yeah, reduce echelon form. So then find solution to the system. That solution is the same. Yeah, so that solution is the solution of the system, original system, right? The takeaway point, write your system in matrix form. If you have a system like this, write that system in matrix form, makes matrix form, sorry. Then consider the augmented matrix. Reduce this augmented matrix to something, yeah, something simpler to deal with. Yeah, something simpler to deal with. Using performing raw operations, right? Raw operations. Then we have a reduced matrix for augmented matrix. Then find solutions. How do you find solution? Yeah, so here you can system, write this in matrix form, or let's say, yeah, let's yep, so here I can perform raw operations here. So like this. Yep, so then I finally get this reduced echelon form. Here this consists of both both coefficient matrix and right hand side, right? Yep, so we get this here zeros, no x term, and no x term here, no y term, right? Haha, I have only z. Yeah, you can find variable z. We start from the bottom to top. So because here we obtain an equation which is flowing always in yeah, z variable. Yep. So floating only z variable. This equation has only, yep, so has only z variable. Yeah, we start from here. First find z variable, which is 2. Yep, so then the second, if you go to the second equation, consists of y and z variable, but you already found value of z, right? Substitute that value of z into this, then you can find y. Now you have z with y, so here you have three variables floating in this equation. Yeah, so you already know value of z and value of y. So why not substitute those two values into here to find, yeah, x. So this is called back substitution. So the summary, write the system in matrix form, right? consider the augmented matrix, right? Consider the augmented matrix. Reduce this matrix by performing row operations to something, yeah, yeah. So reduce to echelon form, or at least row reduce echelon form. Echelon form is enough, I think, right? So yeah. Then you have yeah, so this would be your coefficient matrix, and this is, yep. So you can separate out. Yep. So this is right hand side. This is new right hand side. That dash. And so how do you find the solution to this simple system? Yep. Yep. Start from the bottom, right? Start from the bottom. First find this variable, this unknown variable. Then substitute that unknown variable into the previous equation. Then you can find the other unknown variable, then substitute those two values to get that, like that. So this is called back substitution. First, reduce the augmented matrix using, yeah, Gaussian or using operations. Yeah. So right, echelon form. Yeah. Yeah, using row operations. Three row operations. Yep. So these are three row operations. The change. Yeah. Yeah. So this. Yeah, I explained. So, and how do you obtain solution? Yeah. Use. So how do you start from the bottom equation, bottom row, and obtain the solution? Yeah. All right. It's 9:30. Yep. So I will do. Yep. So let's use our Octave. So yeah, to do those calculations. So clear, I will clear everything, clear memory as well. Yeah, you can do with me. Yeah, memory is clear. Right? Yes, this is the history, memory, no memory here. Now I define a matrix. Augmented, this would be my augmented matrix. Oh, before that, yeah, because you are small kids, yeah. Otherwise, some people get confused. I will enter the coefficient matrix first. Yeah, this is my coefficient matrix. Yeah, so then I will enter my right hand side of the system. Yeah, this is my right hand side. The second one. Correct. Third. Yep, so if you look at the coefficient matrix, how many rows? One, two, three. Yeah, three equations. Yep, three equations. Now this is my right hand side. Yep, so now I have to consider the augmented matrix. Yep, so I will combine both A and B. It's my augmented matrix. Okay, now I perform row. Yep, so I perform row. Yeah, I will perform row. So I will reduce this matrix to echelon matrix, or row reduce echelon matrix. So at least echelon matrix. Yeah. So echelon matrix is enough. So do you remember in first year? So I have, so yeah, so echelon. So row operations, three row operations. So this is the echelon form, row echelon form. Yeah. So getting 111 and also. So this is the goal. Row reduce echelon. What's the row reduce? This is row reduce echelon. or reduce echelon, all are 0. This is row reduce echelon. This is echelon form. Row, yeah, echelon, row echelon form. Remember, yep. So this could be any number. So at least we can obtain this. So at least this would be fine if you have this reduce row echelon form. Yeah, you straight away you don't need to do back substitution. So this is the solution. This is the solution. But if you have echelon form, so you have to do back substitution to obtain solutions. Got it? Did you understand that? Yes or no? Yep. Yep. So let's get rid of this bugger here. Yep. So how do you do that? Yeah. So I multiply the first row by -3. Then add the resultant one to the second row, and the resultant and the second row will be replaced with that. Okay. So let's so second row, it has a name, augmented. Oh, I don't like to type, this is too long. Second row, second row, second row. So I do the row operation on second row. So replace. So what is the operation? -3 times the first row, aug first row, first row, and add with and add to the second row, add to second row. Yes. Here we go. So I multiply the first row by -3, and add that to the second row, which is replaced the second row. Second row is replaced with that. Okay, so let's see. Here we go. CU, so we have 0 here. So I would like to get 0 here. I want to kick out this guy. This time I will perform row operation on third row. What is the operation? I multiply the first row by -2, and add to the third row. The third row is replaced with that. Third row is replaced with that. See you. See you. So we invited these guys here. So like that, you can perform row operations. So then this guy. So now so all elements under the pivot element are equal to 0. Now we go to second row. So what is the first non-zero element I encounter? So this is the first non-zero element I encounter. So this I choose this as my pivot element. This is my pivot element. Now I will reduce, I will get rid of all other buggers below this pivot element. This is the only bugger. Yep. So if you like, yeah, let's change the sign of this. If you like, you don't need. Yeah, you don't need. Yeah, you don't need. Yeah. So yeah, I would like to get rid of this burger. Yeah, do that. Yep. So this time I will do operation. Perform row operation for the last row, and I multiply. Yeah, yeah. Two. I multiply the second row by positive 2 by plus 2 and add that and then to the last, yep, right. Then the third row is replaced with that. Yeah, see, yep, like that. Yeah, so yeah, this is your actual, yep. So you can change it. Yeah, sign of you don't need, yep. Yep, so yeah, this is your coefficient matrix now. And this is your new right hand side, and here hidden x1 x2 x3. Yeah, I will write here 1 2 1 0 -1 -2 0 0 1 x1 x2 x3. And this is my new right hand side, 1 0 1. Here, very easy to find x3 negative. Start from the bottom, right? Start from the bottom. This row multiplied by this unknown vector, then x3 would be -1. Yeah, if you have x3, what was x? Yeah, so x3, so this one is x2, -x2, plus x3 is -1. -2, right? Yeah, -2. Oh my God, -2, which is equal to 0 to, yeah, so yeah, x2 is 2, right? And what is x1? x1, hurry up, x1 is this one. Is x1 would be x3, so 2, 1, x1 would be 2, okay, minus 1. Okay, -2. Yep, -2. Yeah, -2 to -1. Yeah, -2. Let's see. Yep. So, all right. So, yep. Let's find inverse of Mantel matrix from. I want to read this coefficient matrix, right? What is that? What is that? From column any row, from column 1 to column 1, 2, 3. So times times up my the right hand side, the column, the last column, last column. all, all rows, dash, y, C. All right, x1 is -1, x2 is 2. Yeah, so if you find the what is the original one, yeah, original one. Let's find that. You can, yeah. So some people use this notation as well. Yeah. So this is the original. Yeah. So like that. Yeah, you can stop recording.